Hello everyone and welcome. And today I will be giving you a brief overview of our Elite Power Simulator. To find the tool, head over to the Design tab in the header found anywhere on onsemi.com, and under Tools and Software, you'll see the Elite Power Simulator. A MyOn account is required, however, once created, you will have full free access to the tool. To run a simulation, go ahead and select Simulate Now. From the first page, you'll see in the header a user guide, an application note to enhance your knowledge of the tool, our Plex models, access to the self-service Plex model generator, which I covered in a previous tutorial video, as well as a support link to our support email. For the applications, we have 32 different topologies available between automotive and industrial segments. However, today we'll be focused on the industrial case. You have converter topologies ranging from AC to DC, DC to DC, and DC to AC instances, and all of the most common ones that you might find. So some examples for AC to DC would be an active front end, a boost PFC converter, classic bridgeless PFC, totem pole bridgeless PFC converter, or a Wiener rectifier. For DC to DC topologies, you have things like boost converters, synchronous boost converters, flying capacitor, forward converter, LLC, dual active bridge, and CLLC. And under DC to AC, you have things like full and half bridge inverters, Herrick, H5, H6.5, and multi-level inverters. However, today we'll be focused on a simple boost converter. In the next section, you will select the device as well as the voltage and the power rating of the converter. We'll stay with the automatically populated 400 volt input and 800 volt output, but we'll increase the rated power of the converter to 5 kilowatts or 5,000 watts. For our switching device, this can either be a silicon carbide MOSFET or IGBT, and in this case, we'll select a silicon carbide MOSFET. And for our diode, this can either be a silicon carbide diode or an ideal diode with zero capacitance. From the drop down here for our MOSFET, you'll see all of the devices that we have recommended for this converter, and you'll see here that we only recommend devices whose breakdown voltage exceeds this maximum voltage that you'll see in the converter, which is going to be 800 volts. Therefore, for this converter, we'll only recommend switches with 900 volts or higher. However, today, we'll focus on our 22 milliohm TO247 4-lead 1200 volt M3S silicon carbide MOSFET. And for our diode, we'll select a 50 amp rated 1200 volt silicon carbide diode. Under the device configuration tab, you can see the MOSFET that we have selected, as well as the diode and their corresponding data sheets and product pages. You can adjust the number of parallel devices per switch location, which you may want to increase to handle higher power converters. You have the turn on and the turn off external gate resistances automatically populated as well. And you also have the option to select your loss model, either the nominal loss data or best case conduction loss, worst case switching losses, or worst case conduction loss, best case switching losses. And this is explained in the previous self-service Plex model generator introduction tutorial video. In that tutorial video, we also created a custom Plex model to upload into this exact simulation. And we'll go ahead and we'll upload that model to this simulation. Go ahead and hit select model. And from here, if you go to wherever you have the file downloaded, it'll be in a zip file, which you will extract to your preferred location. select the file, and then go ahead and open. Once populated, you will see all of the different values that we built the model based off of, such as our tested temperature conditions, 25 degrees Celsius, 75, 125, and 175 degrees Celsius, as well as the voltage and current conditions that we tested at 600 volts, 750, and 900 for our load voltages, and 0 amps all the way up to 50 amps in steps of 5. For our circuit parameters, you have your inductance in millihenry, you have your load capacitance in microfarads, and you have your switching frequency in kilohertz. Under the cooling tab, you have the ability to add the thermal resistance of the grease that's applied to your MOSFET as well as your diode. You also have the option for your heatsink model either to do a fixed temperature value or a custom thermal impedance model based off of either a Foster or a Cower network. However, in this case, we'll just do a fixed temperature heatsink model at a slightly higher value, 50 degrees Celsius. Finally, to the simulation tab, in order to run the simulation, just go ahead and select Simulate. And the DC to DC converters run very quickly. It's a matter of seconds. On the right, you can see the source voltage and current values. Under devices, you can see the switching currents and voltages. And you can also see the junction temperature and how it fluctuates with time. Another feature of the tool is from any one of these curves, you can export the data and view it in closer detail. On the left, you have a system overview for your input and your output voltage, your duty cycle, your power rating, your switching frequency, your inductance and capacitance. You have the maximum junction temperature for your FET as well as your diode, which you can see is well within the 175 degree maximum for either. And you have a detailed overview of your losses, such as your switching losses, your conduction losses, your diode conduction losses, your combined losses, and then your expected efficiency. Further, you have the switch losses breakdown, which includes the turn on losses, turn off losses, forward conduction, reverse conduction, and body diode conduction losses. One unique thing about the tool is the ability to hold a result and go back and adjust any of the parameters as long as you keep the same topology. You can go back to device selection and select a different MOSFET and compare a higher RDS on device, or perhaps you wish to adjust the switching frequency in order to reduce the size of your magnetics and your passives. So in this case, we'll double the switching frequency from 20 to 40 kilohertz and see how that affects our losses, keeping everything else the same. So we'll select Simulate again. And from here, you can now see with this higher switching frequency how we do have higher losses. Your switching losses and your conduction losses compare, and your efficiency as well. You can see all of the previous traces that you have added here under traces, and you can delete or add more. Or once you're finished with your simulation, go to Next Step, where you can print this output that compares these different test conditions. For more information on how to use the Elite Power Simulator, head over to onsemi.com for access to, again, user guides, application notes, and to run the simulator yourself and see how your design performs with our latest onsemi transistors. Thank you, and until next time.